All right, so today we are watching Infinity Isn't a Number, It's Something Much Weirder.
This is a problem that can break the entire idea of infinity. It starts with a vase and infinitely many numbered balls. Let's start 1 minute before noon. I put balls 1 through 10 into the vase. Then I remove ball number 1. 30 seconds before noon, balls 11 through 20 go in, and I take ball 2 out. 15 seconds later, half the way to noon, 21 through 30 go in, ball number 3 out. We keep going, each step half as long as the last, forever. At exactly noon, after infinitely many steps of adding 10 balls and removing 1, how many balls are in the vase? The answer is infinite.
There are different sizes of infinity. I do know that. You can do that in different ways. You could do every other one. You could do every prime number. There's an infinite amount of prime numbers. We don't know for sure. There's an infinite number of multiples of 6. There's all these different infinites that are different sizes. There's an infinite number of real numbers. There's an infinite number of numbers between 1 and 2. You know, you could have 1.1, 1.11, 1.111, 1.11, you know, 1.112, like you can go on forever. There's an infinite number of those quantities.
Also 0. Both are correct at the same time. This is a video about how infinity doesn't mean what we think it does, and what happens when our brains try to make sense of more than everything. Hey smart people, Joe here. How long does it take for infinity to happen? That question sounds kind of ridiculous. Like if you ask ChatGPT to do a Vsauce impression. Can never do that. But to prove it, just imagine walking across a room. First you have to cross half the room, then half of what's left, then half of that. Infinite steps, each step half as close to the finish, but never there. Yet, here I am.
So yeah, that's a common paradox where, you know, if you half the distance every time, you take half the distance all the way up until the end distance, you'll never reach your final destination. But in math, we do have infinite sums. You have sums to an infinite series of things. If you take all the halves all the way from 0 to 1, it still equals to 1 because 1 is the limit. Obviously, a limit means that you can never reach it, but if you take the infinite sum, that total of halves is going to equal 1. And in reality, you are obviously going to be able to reach that destination. So it is a paradoxical thought experiment, but in practice, it doesn't matter that much.
Across the room. This very problem was devised by the Greek philosopher Zeno 2,500 years ago. He wanted to prove that motion is impossible, which we know is silly because it is obviously possible. Look! Zeno was right that there are infinitely many steps, but he was wrong that they add up to infinite time. You see, if each step keeps getting shorter fast enough, infinite things can fit in finite time. Half a minute plus a quarter minute plus an eighth of a minute, so on forever. That adds up to exactly 1 minute. Infinite steps, finite time. And completing infinitely many operations inside of a finite window, that's what mathematicians call a supertask. You can't do a supertask with your real human hands, but the mathematics works. And that math forces us to ask some pretty weird questions about how infinity is different from, you know, non-infinity. When you take supertasks seriously, infinity starts revealing some deeply strange stuff. Let's say that you run a hotel with infinite rooms, and every single room was occupied. A new guest shows up at the front desk. Instead of telling them no vacancy, just ask the guest in room 1 to move to room 2 to room 3, and so on, forever. Now,
this is like an interesting problem. I've heard this one before because theoretically this should work. You have an infinite number of rooms in your hotel and each person just moves 1 down and it's able to work because, you know, there's no end to infinity. There's no person at the very end who doesn't have a room to move to. So you can keep adding guests to your hotel. So it's for the same reason that you add 5 to infinity, it still equals infinity. And I don't even think equals is the right word, but you still have an infinite number of things when you add finite numbers to it.
Room 1 is free. The hotel is still completely full, but you've still added a guest. The rooms represent an infinite set. You can add to the whole without changing the size of the whole, and both are still infinite. This sounds ridiculous, but this isn't a glitch in the math. So what happens if 10 guests arrive? You don't need to break a sweat.
Same
Just
thing.
get on the intercom and ask every current guest to move to the room 10 numbers higher than theirs. Room 1 to 11, room 2 to room 12, and so on. Forever down the hall of infinite rooms. But now rooms 1 through 10 are empty, and all 10 new guests get a bed. And the hotel is still completely full, just as it was before. So what if an infinite bus arrives, carrying infinite guests? Trickier, but you have a move for this too. Just ask every current guest to move to the room that's double their current number. Room 1 goes to room 2, room 2 goes to room 4, room 3 to room 6, and so on. Now every odd-numbered room in the entire infinite hotel is empty. And since there are infinitely many odd numbers, every passenger on the infinite bus gets a room. We've fit infinity inside of infinity. Now let's say
So I guess that's why it's not a number, is because it doesn't change. There's no specific quantity of infinity. You can alter infinity by adding things to it, and it doesn't change the concept itself.
inside every one of those infinite rooms is a lamp. 1 minute before noon, you flip the switch to on. 30 seconds before noon, lamp off. 15 seconds before noon, on again. The flipping doubles in pace forever. We flip the switch infinite times before noon arrives. So, at exactly noon, is the lamp on or off? There is no right answer. Not because we haven't figured it out yet. There literally isn't an answer. When we get to noon, it doesn't end on, it doesn't end off. It just ends. This is one of the things that makes super tasks so weird. They can end without a final ending state. Problems like these introduce ideas that are hard to accept because they don't match our experience in the real world, but they are still just as true according to mathematics. Infinity isn't one thing, and some infinities are bigger than others. The whole numbers go on forever. 1, 2, 3, 4, etc. And the fractions go on forever too. But we can pair every fraction to a whole number, 1 to 1, with nothing left over in either set. So these infinities are the same size, but the decimals don't work that way. There are too many of them to match these infinities. In the 1870s, mathematician Georg Cantor proved this, and his argument is an elegant one.
The decimal infinity is larger than the other infinities, but that's like a concept that doesn't that's very hard to comprehend with like the human brain, because infinity means it goes on forever. So how can one forever be larger than another forever? It only works because of the things you match it to. So you can think within a certain set of digits of that infinity how it would work. But when you scale it to forever, even though we know that there's not going to be a point where the whole numbers catch up to the decimals in the infinite set, we still can't ever count them all out to see and prove that, because they do go on forever and it's impossible to count. So it's such a interesting concept.
Suppose that you claim to have a complete list of every decimal. This one, and so on. We can attempt to match every decimal number 1 for 1 with every whole number, but I can always find a decimal that's not on your list. Take the first digit of your first number and change it. Take the second digit of your second number and change it. The third digit of the third, and so on. The decimal I've built differs from every number on your list in at least one digit position. So your complete list of decimals isn't so complete after all. Cantor showed that whatever infinity you're looking at, you can always construct a larger one. The decimal infinity is bigger than the whole number infinity, but there's an infinity bigger than that one too, and one bigger than that. The ladder of infinities goes up forever. Infinity also breaks arithmetic in a way that honestly kind of bothers me. Take this infinite series. 1 minus 1 plus 1 minus 1 plus 1, and so on. What does that equal? Well, group the terms one way and you get 0. But start from a different grouping and you get 1. We can even rearrange the math in a different way. Let's subtract this series from 1. Do some basic algebra to rearrange things.
That's so weird.
And the answer ends up being 1/2. It's an equally valid answer, but for certain
I remember doing this in like high school math. These infinite series were something that I could never get my head around. I struggled with it so much. And it's a totally different type of number. Like it's a totally different way of thinking. And that's something about math that's so fascinating is, you know, you have things like imaginary numbers, infinite series. There's just so many different ways to think about numbers that don't really mesh with each other too well.
infinite sums, the order that we add things up changes the result. Which brings us back to the vase. This thought experiment was originally devised by mathematicians John Littlewood and Sheldon Ross. It's known as the Ross-Littlewood paradox. And it's a paradox because two completely true lines of reasoning can give us completely opposite answers. Recall that at every step we add 10 balls and remove one. And each step is done in half as much time as the one before. A net gain each step of 9 balls. So after 10 steps, roughly 90 balls. After 100 steps, 900. Run that out over infinitely many steps, and the number of balls in the vase is infinity. Then again, maybe the vase is empty. At noon, which balls are in the vase? Let's pick any ball. Ball 47. That went in during step 5, and it came out again during step 47. Ball 1 left in step 1. Ball 1000 left in step 1000. Name any ball and I can name the exact step when it was removed. So at noon, after infinite steps, there is no ball in the vase that wasn't eventually taken out. But suppose instead of removing the lowest numbered ball, I change which ball I take out each step. Same deal, 10 balls in, 1 ball out. But now, instead of removing ball 1 in step 1, I remove ball 10, the last one that I just added. Step 2, balls 11 through 20 go in, ball 11 out. Step 3, balls 21 through 30 are in, ball 12 out. And so on. Now which balls are left at noon? Ball 10 was removed in step 1. Ball 11 in step 2. Every subsequent ball gets pulled out in some future step, except balls 1 through 9. Nobody ever touches them. No step exists where they get removed. Exactly 9 balls remain at noon. We did the same process at the same rate. 10 in, 1 out every single step. But by changing which balls I remove, the answer went from infinity to 0 to 9. The vase doesn't have a true answer because the answer is whatever the process says it is. All of these arguments have sound logic. The secret is that each scenario in our paradox is
I think it's hard because when you're dealing with infinity, it's hard to use logic because something going on forever doesn't exist in our real world. Like we don't even know if the universe goes on forever. It could be finite, but maybe it does go on forever. But it's just something where, you know, our local understanding of how things work, it doesn't come up with a satisfying answer when we're talking about something like infinity, where it's just so alien to us. It's something we've never experienced, and our math has no way to really deal with it in a easily comprehensible way. Like multiple answers for something doesn't feel right.
actually tracking different things. One watches the size of the set at each step and then extrapolates forward. The second traces the fate of individual balls. And the third shifts how we group things to get a totally different answer. In truth, we can't have an answer for what happens after infinite steps because there is no final step at all. Asking what's in the vase at noon is like asking what's north of the
Yeah, so that makes sense. So that's like a similar thing to like the hotel thing. You obviously would never have an instance where the last person in the last room wouldn't be able to move over. So you can just keep on adding. So there's not going to be a final step, and you're not going to get a point of full vacancy in that hotel, and you're not going to get a final state for these like infinite series. You're not going to get a final state for the infinite vase problem or the infinite lamp problem, because you can always add more steps. There's no final step.
North Pole. The question makes grammatical sense, but doesn't refer to anything real. The vase and balls paradox doesn't really have a solution because the fact that it has many solutions is the solution. This is what infinity actually is. not a very large number, not the number at the end of the number line. I've learned to think of it as a direction, a process, something that you can approach forever without ever arriving. Treat infinity like a number, and it will fool you. Mathematics can describe what happens at every individual step. It's a beautiful machine that can take our brains right to the edge and then show us that the edge isn't there.
Hey, yeah, so infinity doesn't have like a direction to it. You can't count up to it. You can't count down from it. It's an action you can take. You can keep taking. And you know, an action doesn't have an end because you can keep doing the action. Man, certain things just break my brain. This is one of them. You know, you can logically sort of think about it, but it doesn't feel satisfying to think about infinity at all. There's nothing satisfying about it. It never feels familiar no matter how much you think about it. It's just one of those things. But thank you so much for watching. I will catch you on the next video.